been in this meeting twice. This is the second time here. So I hear a lot of talks on antibodies. Very little attention has been paid to antigens. I figured this thing are related. So I want to put some thought on this one. Anyway, my name is Jianxin Li. For people who cannot pronounce that first part of the name, go by Jason Li. This works very well. So call me Jason Li. And I'm the CEO, official title is the CEO of Proteintech, but I'm more of a technical person. So my official job in the company is a tech support. So if you call Proteintech, I'd like to speak tech support, likelihood you got Jason Li there. So we have a lot of branches now, and Chicago is our headquarters, Wuhan is our production facility, and Manchester is our marketing base, Tokyo and Germany, for instance, Australia, Singapore. We also just bought a company called HumanZyme, which makes wonderful human protein, and that's why I want to talk about protein, the antigen. How do I get to the next one? But before I do that, I want to continue with a lot of Chinese characters there. Because my last slides in last talk was that the current crisis of antibody market partially was blamed onto the force factors called the monkey wrench, the random investment from real estate money, which is true. A lot of money in real estate in the territory of China, trying to filter into some other area because everybody sees the danger of collapse of the real estate market. So whoever has made a lot of money want to move out. And a lot of money has been invested into companies. And we just did a really quick count of all antibody companies in China that sells antibody in their website. This is 174 of them. And just in two cities, one is called Wuhan, one is called Beijing, each one has 37 of them. So the good news is you can find a place to buy antibody. The bad news is you really don't know what antibody that is, that one you bought. So having that in mind, our job, being in the market for many years, Proteintech has been existing since 2002, is really trying to shed light for the consumers, for the scientists, on how to select antibody. It's also, we take as part of our responsibility, being such an old guy, to teach newcomers how should antibody be made, and how should it be validated. So, I teach immunology as a university professor. I've been doing that for years. One funny thing I noticed is we have a circular definition of what is antibody and what is antigen. So when you look at Janeway immunology textbook, which is very classical, all medical schools use it, its definition of antibody is a group of proteins, each possess a unique antigen specificity. And then you say, what is antigen? Antigen are substances that bind to antibody. So you go, whoops. It doesn't work that way. It's a circular definition here. But actually, that shows how important these two are linked. Because you are really trying, in our work, we're really trying to generate an antibody that's specific for that antigen. So for that specificity, it is very much linked, right? So today's talk, I want to jump from the marketplace to science, the antigen. So the title would be antibody depends on the antigen. I want to say to produce an antibody, it depends on the authentic antigen. And to validate antibody, it depends on an antibody in the real sample. And to use an antibody, because I'm a tech support, I get phone calls all the time, right? So I teach them how to use it, so it depends on the available antigen. You have antigen, it's not available, it's not going to work. So I'm glad the time just touched on the antigen importance in your talk. I'm also glad people talk about the chips here. So let me look into each one of them. So top one is to produce antibody depends on the authentic antigen. Now there's a disclaimer I have to say, because our company since 2002 has been dedicated to make antibody with proteins. So we go along human genome. Whatever the gene bank publishes, we make it into a protein. So obviously I'm biased towards protein is better. Protein is better antigen than peptide. But you don't have to believe me on that. Please don't. So anyway, I say whole protein, it will be the one that maintains the secondary structure, so you can make a better antibody out of it. The glycosylation side is a huge interference in making antibodies. And tertiary conformation are very important to make an antibody that against the native form of target, of protein. So we started with this one, right? This is one of our star antibody called TDP43. And as you can see, the antigen binding place, I have it highlighted. So we mapped the epitope to 6 amino acid, not us, somebody else, the scientist. And that's right over there in the 3D structure. You can see it's a helical structure. And how do I make this move? Oh, it moves. All right. So you can see it's really in an ideal location as an antigen epitope. It's a helical structure, very stable, so rarely changes. Number two, it's on the surface, so anytime the antibody can get it. So the fact is, this antibody can do almost everything. It's a monoclonal antibody. We do make both monoclonal and the polyclonal. I hope we're not going to be out of business. So the Hendra predicted that there's no more future. They actually work very well. But this one is monoclonal, to your point, Alejandro. And it does everything. It does immunoprecipitation, does Western blot, does immunohistochemistry, does immunofluorescence, almost every application book. Why? Because it's here. Helical structure, hard to modify, hard to disrupt, and it's there. And the antibody was generated with whole protein. Now, if we remember our before I say that, so obviously I did not reset my slides well enough. It is very hard trying to get that small domain of protein into a peptide and still maintain your helical structure. It's an engineering challenge to say, all right, I'm going to make small synthetic peptides and do that. Most time you get a random coil. You know what happens with random coil is you have different MHC molecule binding to it. Each time it binds to it, it's a different shape, and different shape give you different antibody. You're going to have a huge trouble to get a lot-to-lot consistency. We never have that trouble. Proteintech, from beginning to the end, out of 12,000 antibodies we made, we sold most of them already. As Alejandro predicted, you're going to have a new animal, which we did. We never have one that we cannot reproduce. And that is definitely not reproducibility. Why? Protein plays one of the most important roles in this case. Because this is a randomly chosen article talking about conformation, right? Most time you get random coil, but sometimes you get a secondary helical structure. It is very hard to get one. This whole article is about making a helical structure, if you want to read it. Because if you think about it, in our entire process of making an antibody in your body, there was never a single moment that you have a free-floating peptide. You have a protein to start with. It is not free, as I told you. You get it uptake by the cell into the phagolysosome or endosome, and in the end into the lysosome. It digested into a small piece. But that small piece was never free. It was bound by protease. And then what happened? It transported to MHC class 2 compartment. There's a special compartment for it. And transferred to the molecule MHC. And it was never free. So because it was never free, the secondary structure was maintained along the way. That's why when you make an antibody with a whole protein, it's far, far better. But still, it is a struggle, even with a whole protein. I'm talking more about our failed cases to you than our successful cases. Instead of showing you glorious IHC, immunofluorescence, all those pictures, I rather want to talk our failure. Because when I was started as a PhD student, I was trying to do a chemical synthesis, making the compounds, adding a fluoride to a second carbon of a fatty acid. Took me 6 months, nothing worked. I was frustrated like hell, but my lab mate, a senior one, called me down and says, Jason, you only learn things if things doesn't work. Because if you fly by, you don't have time to think about it. Here, so we only learn things when things didn't work. So I want to talk more about the failed examples than successful examples. Protoplanning is a very important protein. There's a famous antibody to it, natural purine, D240, monoclonal, and been used to diagnostic with a lot of cancers. Extremely difficult to make antibody to it because it's such a highly glycosylated protein. You look at all those possible glycosylation sites. So we tried. We tried to use the first 100 amino acids from 100 to 101 of this protein expressed in a GST fusion. Totally failed. Nothing. The antibody does not even come out to bind anything. Then we tried amino acid 101 to 238. That's all second half of the protein. We expressed. We can get an antibody to do Western blot, but we can't get it to do anything else. It doesn't work. Until we get the full length protein going, now we get an antibody that does both immunohistochemistry. The reason is most glycosylation part is concentrated to the front end of this protein, and the second part it doesn't. We thought just use the second part would work. It didn't. Apparently, they have affecting each other in terms of secondary structure. So unless you use the whole protein. But unfortunately, it is expressed in bacterial, so it is not glycosylated at all. So the structure isn't that great. So the antibody, even though we have it, is not a great antibody. Still, far below the level of D2 antibody, right? And then we try other things. There's another example. We try to make antibodies. Actually, this is a case where we are making proteins. So we're making interleukin-7 proteins expressed in human system. So we take the whole lysis and look at the expression level. And then we realize our interleukin-7 antibody does not recognize, this is a PTG antibody, a monoclonal 60206, only recognizes the reduced form. It does not recognize the non-reduced form at all. On the other hand, R&D system monoclonal works beautifully here, recognize native form. It does not recognize the non-reduced form. Except our polyclonal, it does both. Okay, Alexandra, this is a polyclonal. So it works very well. Obviously, it tells you one thing. If you want to have an antibody that can do work in the native form, you do need to have a protein really in native form. Even a bacterial expressed is not going to do the job. So we say, all right, let's do this. Let's look at some example, making more antibodies with human cell expressed proteins. So we say, let's make it against BMP7. We have this 293 cell expressed human BMP7 protein. Let's make antibody against that, see what happens. So this is a screening of clones, all right? All those clones are ELISA positive, by the way. All these clones listing over there are ELISA positive. And then we run the total cell lysate with BMP7 on it for Western blot. And you have two panels. This is with capital acido reduced, without capital acido non-reduced. We got 3 clones over here between 1 and the line that can recognize the native form. We got 3 others that also recognize native form but not reduced form. So apparently, if you're trying to generate antibody with a very authentic human protein, this is as authentic as you can get. Human sequence expressed in human cell lines with human signal peptides by itself exported out to the cultural media. You purify it, no tag at all. We go classical biochemistry column purification. You get it, and you immunize, you get this. So apparently, the conformation of antigen in the tertiary structure is everything. Yeah, it's everything, right? So for that purpose, I said, this is great. Let's just buy this company then. So we bought it, Human Lab. It's a wonderful company. Make best protein in the world. And we just put it in the whole GMP for them. So now everything is GMP. All human cytokines in the catalog. It's fantastic. And then you can expect more of those antibodies will come out, blocking functions. This is protein, why it's good. It is animal-free, first of all, totally tissue culture. It's xeno-free, it's in human. It's tag-free, it's endotoxin-free, authentic glycosylation, authentic folding. And for example, I can tell you this, the glycosylation is very different if you have the same protein expressed in CHO cell, for example, we made it in EPO, and have them expressed in human cells. And this is a CHO cell profile, and this is the human profile. It's very, very different in terms of the glycosylation, the sugar profile. And also, when you express in human, the processing, you generally, if you have a protein, you start with a pre-pro, and then pre get it chopped off, you get a pro-peptide, and the pro gets chopped off, you get a mature form. And as you can see, the A and B is from the CHO cell, C and D is from the human cell. And this is reduced, and this is non-reduced. As you can see, it has extra precursor that doesn't get processed well. When you have those things in your antigen and you inject into animal to make antibody, you generally get unexpected results. So a human can process human protein very well. A hamster cannot fold and process human protein very well. As simple as that. And so in order to get a good antibody, you need a good protein to start. And same thing, even functionally can be different. For example, human TGF-beta will work in human T cells, but mouse expressed human TGF or CHO expressed human TGF does not work on human cells. There's even articles in the Nature found at the beginning made a mistake, thought the human is different. People been doing research trying to see what's different between human and the mouse. We're very similar in many ways. And one article comes out and says, okay, well, I found a difference. This does not work in human, it only works in mouse. And then second Nature come back out 2 years later and says, you're using the wrong protein. So that's how it works. So second, to validate the antibody, it depends on real antigen or antigen in a real environment. I'm glad you guys in the whole day is talking about application-specific validation. That's very important. This is very important. I want to elaborate on that. Now we all hear a lot of commercial advertisements say, all right, this is a protein chip or protein array, and my antibody recognizes one dot and nothing else. It could be 1,000 behind it, nothing, no signal. This one recognizes one thing. This is a wonderful antibody. Is it? It's not, obviously. But everybody has different reason for saying it is not. Because you say, well, in IHC we get all this background, it's non-specific binding of that. I'm trained as a biochemist, so I always look at affinity, right? The biochemistry formula. What I'm trying to say is that proteins are not created equal, especially in the abundance. The abundance of protein in cells and tissue impacts the specificity of each of those antibodies. Big way. So this is a very useful database I recommend to everyone. We use all the time, called PAX-DB. It's a collective work of a group with a mass spectrum to show the abundance of proteins inside a particular cell or tissue or species. Right, so it covers human, mouse, and many different species, and many different tissues, many different organs. And as you can see, even with actin, it's only ranked at number 3. It has 21,000 ppm. That's the high amount of protein. And then you look at those no amount of protein we're trying to make antibody against. It's 0.01 ppm. Now you're talking about the 10 to the 7th power difference here. Okay? Now you're trying to make an antibody that sees this guy and not that guy. Right? Being a biochemist, we know there's nothing absolute in this world in terms of affinity. There's always affinity to everything. It's just a matter of how big it is and how small it is. So the gap has to be more than 10 to the 7th in this case, right? Otherwise, it will bind to another one. And if you do a whole bunch of biochemistry calculation, I know you're probably sick and tired of it because you had an exam when you're in the high school or college. But the calculation actually I did for Western blot is what sensitivity of protein can be detected by an antibody. The conclusion, if we jump straight to that, is for most antibody has affinity of 10 to the 9th to 10 to the 11th. Some goes as high as 10 to the 12th. Therefore, the detection is 0.1 nanogram to 1 picogram. If you believe all my calculations, remember I'm a math name also. I'm good with math. So that means if an antibody has an affinity 10 to the 9th, it binds to 1 nanogram of the stuff. What if this same antibody has 10 to the 3 of the power to another protein? It so happens the other protein is 1,000,000 times more than this guy that you intended to bind. Now you're in trouble. So remember I'll skip that. Remember in this chip, almost, if they did a good job, almost all those proteins are equal amount, right? It doesn't happen in the cell. I just showed you, there's 10 to the 7th difference there. So whatever you say is a specific here means nothing. So I'm trying to educate my customers that it means nothing. But they say, they said it on the magazine. Yes, on the cover. No, you can't argue with that. It's on the cover. So I want to share with you my own data. It's a very, very secret data we did on our own statistics, okay? This is our success rate. Now I'm showing you everything of this company. When we started this company, we do nothing but bury our head in the sand and just make antibodies, one at a time, goes along the gene bank number. Okay, first gene bank number 1, gene bank number 2, gene bank number 3. We just keep a blind eye making them. After about the 10,000 of them, we say, oh, what did we do? Let's go back and look at them. So we just start doing analysis on it. And we start correlating the abundance of a protein to our success rate. And we classify each one of them target. And this is the success rate of a first round experiment. Let's say you just make the antibody once, the first time. The way we do it is each year we go up 4,000. 2,000 successful, 2,000 failed. Put it aside, forget about that 2,000, take another 4,000 new one, new gene number, and making it. 2,000 successful, 2,000 out. And then when we finish everything, we come back and say, okay, let's pick up those 2,000 failed and do it again, one more round. So this represents the first round, okay? First round success rate. 33 of them are very high abundance, 2 times 10 to the 7th abundance. And it has 91% success rate. You can't fail with it. You make any antibody, it will bind to it. There's so much of it. You don't need a very high affinity. But over here, you see this thing goes down all the time? All the way with the abundance, very good correlation. And when you get down to the 500 copy below, we did 2,000 of them, and we only have 41% success rate on the first one. They're all good antibodies. If you load a beautiful fusion protein or purified protein, it will bind. You put a mixture protein, it will bind. You put on that chip, it will be specific. It simply does not have high enough affinity to the real amount in the real sample. So the only way we can do it is remake them, right? So we say, all right, failed, what the heck. The good news is our company does not count the output as your performance. You get one antibody, you still get this much salary. You get 100 antibodies, you still get this much salary. Not a problem. It's never a problem. It's the quality of it. So we redo it. This was the one failed, very small percentage according to the database. So in the database, I forgot to tell you, this y-axis represents the number of proteins, unique proteins, gene IDs. This represents its abundance, ppm. So when the ppm gets down here, in our experience, when the ppm is below 0.3%, 0.3 ppm, your antibody will require extraordinarily high affinity, otherwise you're going to get failed results on the real sample. And so this one is really, really small. Now, of course, there's also different tissues. So here you can say, oh, wait a moment. You said 0.3 is here and it's below 0.3, but here says 33. That's some specific tissues. So we're talking about in certain tissue we could get our hands on to assay. Sometimes we just can't get those, like a human brain. It's very rare commodity. So anyway, you can see we used half of the protein did not work. We used the whole protein, it worked. And did not work, nothing here, and it worked. And same thing for this guy. We used this part of the protein, did not work. We used the second half of the protein, it worked beautifully. So it's really, you have to look at the structure. Unfortunately, at the time when we make it, most of the protein does not have X-ray structure available. So we can't look at it and say, yeah, that helical looks good, let's include that part. We don't have that data, so it's really not enjoyable. Now we go back, we can see the example of it. Okay, I won't skip that. So 3, to use antibody depends on the available antigen. This is also interesting. I'm tech support again. I get phone calls. All right, we have a very good antibody. Our complaint rate is 0.4%. With the open return policy, we only have 0.4%. And, but I'm tech support, I will talk to them. This is the most common question I got, right? 2 types of questions. I have no fat. I have too many fats. one or the other? That's the most common question you get. So my question to them, my first question to them is, did you check the PAXDB on the tissue or target you're trying to use? You don't have to tell me, you go check yourself if you're doing confidential work. And they usually tell you, and I look at it, I said, maybe this thing is not going to work. Go Abham, they probably have antibody from someone. Because our affinity is definitely not this good. Our affinity is definitely not this good to detect something in such a low amount. It's because in the PAXDB it says non-detectable. If it's non-detectable by mass spectrum, for God's sake, mass spectrum is very, very sensitive stuff. So don't do it. Find another tissue to do it all. But if it is a reasonable tissue, and you still get too many bands or too little bands, this is another question I ask. What type of Western blot membrane are you using? He'll tell me, oh, am I using natural cellulose? Most people use natural cellulose. It's fine. There's nothing wrong with it. Oh, by the way, disclaimer again. I have no association with any membrane company. So I'm not preferring one or the other. So what it is? They said one. Okay, I said, well, let's look at this. There's a PVDF membrane. It's an organic matrix. It binds to protein through hydrophobic force. And there's nitrocellulose. It's fully charged with all different charges. It binds protein by hydrophilic force, which is most likely charged with amino acids. If it is an antibody that's generated against the general protein, you bet an MHC molecule will pick the hydrophilic part because it's also on the surface. And the antibody is going to bind hydrophilic. In 99% chance time, it's fine because there's plenty of antigen goes around. The membrane is not going to compete with the antibody. But in small chance, when the antigen is really rare, this thing happens, right? So you have an antibody, you have a membrane, you have a protein, you have nitrocellulose membrane, and the triangle indicates charges. So the thing binds to them by charges, right? And the antibody will bind them fine, right? Oh, no, I'm sorry. This one I should have flipped. I made it wrong on flight. But it can't bind, it's competing. But if this is a hydrophobic membrane and the protein binds to it through hydrophobic domain, all the charge group is available, then the antibody will be able to bind them just fine. So this is happening in very rare case, but again, your tech support, you only deal with very rare cases. So it turns out 90% of calls can be resolved this way. Keep going. And we did an internal experiment on this, on purpose. We made an antibody with hydrophobic peptide. Remember, we always use protein to make antibody, but this case, let's say try it. So we made two antibodies, right? And I just want to focus on this one. That is, works on NC, but not work on the PVDF. And I want you to look at those guys that works on PVDF, but not works on NC. And let's look at its sequence, right? And you can see that it's working better on PVDF, right? You have a very nicely charged D, a lot of Ds, right? But the one does not work on PVDF, works on the NC, only have charges in the end, but the majority here is hydrophobic. So when you have an antibody that's against the hydrophobic domain, it doesn't work very well on PVDF. When you have antibody against the hydrophilic domain, it doesn't work very well on nitrocellulose. Fortunately, most antibody in this world are against hydrophilic groups, and with minor amount coming from certain peptide companies against hydrophobic. So that's the good news of it. So finally, I know it's about 5 o'clock, it's dinner time. So I want to put a conclusion here. It's communication, communication, communication. It's antibody business is all about communication. Transparency, transparency, transparency. Antibody business is all about transparency. I'm glad to see transparency on Andrew's slides too. I'm sorry, I'm just picking on you today. As stated in this beginning of this talk, right? Making each antibody, each protein is different. They behave completely different. They have this very unique requirement. So each antibody to them can be used in a different way. Everything is different. So you need to have a straight, direct conversation with the customer. And we need to open this door and open the channel of conversation between antibody manufacturer and the user of the antibody who are the scientists. Thank you very much.
Thank you very much. Time for one question. One quick question, maybe.
What is your experience with large number of intrinsically disordered proteins? Do you still take the whole protein, or would you go rather for folded domains in that protein?
Okay, so out of 20,000 gene bank numbers, unique gene IDs, we finished 15,000 of those unique gene IDs. Out of the 15,000 unique gene IDs, 50% of them were whole protein approach. There are 50. There are another 50%, half of them, we cannot express the whole protein. We totally failed it. We tried, we failed. Either because they have a heavy amount of transmembrane domain, it makes the protein form a huge aggregate. You'll never be able to get it right. And then some of them simply kill the host, so it doesn't work. So those we used half of the protein. But anything above 400 amino acid, we use the whole protein.